Hi everyone. I wanted to do one last presentation today. I've done three already, but they were short little ones. And since I already had prepared all the searching, sorting, and standard template library stuff while preparing for that first set of lectures, I figured I'd finish off the day with a bang. Just get ahead of things. After I've done this lecture, there might be one or two more, two short ones or one really big one. Um, Looking at sorting and searching, and maybe finishing up some more of this standard template library thing. After that, what I'll do is I'll take a survey for everything that we've done in the course, and see what you guys want to go over with when it comes to a review. I'll do a review lecture. Also open up the floor to questions for you guys. So a review lecture closer to the actual exam, but at least you would have all of this sort of ready to go for the next assignment, for all remaining assignments. So we're looking at sorting and searching, and this is for those of you that have done any computer science classes before. You've already done this. Congratulations. Not everything exactly the same, but there's so much in common. This is one of our topics that we love to talk about. We cannot shut up about talking about sorting, searching, and these, algorithm complexity things. Why? Because it's really one of the fundamental things that really made computer science a science, what it made it special. Um, so, just in case I have a comment on this, I'll say it. Yeah, I guess I don't have a comment on it right away. One of the things that why we obsess so much about it is it's one of our early victories. It's one of those things that when we discover complexity, when we discover that there's a sorting algorithm that's way faster than other sorting algorithms, when we find that there is an actual optimal way of searching for something, and we can prove that, we suddenly have a whole bunch of really, there's somewhat low hanging fruit there, but we have these algorithms that we can come up with that are nice and they're clean and they're mathematically correct and they're useful. It's fantastic. When you're talking about machine learning, we have an algorithm that probably gets a bit better than the other one before it. And how does it work? I don't know how it works. It's all probability based. Yeah. Uh, so as a result, we love talking about these early wins, and sorting and searching is one of the big early wins. To the fact that I have a video in here, I'll ask you to watch it versus me just showing you a video in a video. But it's a video from 1981, I do believe, from Ron Becker's lab at University of Toronto, called "Sorting Out Sorting," and it is painfully dated, sure, as you might expect, but on top of that, it is amazing that nothing has changed at the same time. So when we get to that, I'll point it out. But first, I wanted to talk about the standard template library. All of this talking about linked lists and vectors and stacks and queues. It was all well and good. These are the sort of data structures that we have available to us, but they're already done. Like C already has a standard template library, as in you can just use this library and it works. It's kind of nice that way. But we sort of wanted to look at fundamentally under the hood how all of these things were created. But the standard template library is composed of three main things. We have a bunch of container types. That's the generic term for a list, a set, a stack, a tree, a queue, but things, data structures that we can store stuff in. We have iterators, which is a nice sort of abstraction, allowing us to not know how the heck a list, a vector, a stack, a queue, all these sorts of things are actually made. It hides the implementation details. So I used to always ask my students at Northeastern, who knows what an array list is? Everyone puts up their hand. It's a very common Java thing. And then I ask, who knows how an array list is implemented? And everyone puts down their hand. Same thing here. I have no clue how a vector is implemented. I have a guess, but I don't actually know what the code looks like. The point of this, the reason why we made our linked list the way we did, the reason why our shape objects work the way that they do, the way, if we, I'm not going to claim my code is great code, but at the same time, anyway, what you're always striving for is that great code is a tool that you can use, but you don't have to know how it works and if it's worked and it's implemented and created correctly, so that I can abstract away or hide how that the all the gory details, how it was implemented, and just use it. Again, back to our metaphor earlier in the term, I just want to drive the damn car. I don't want to have to know how to put, my spark plugs in or whatever. The doohickey and the doohickey on my car. Okay, I don't know about cars. So I have containers which store stuff, and I have a rough approximation, a rough idea of how it's storing stuff, but I don't want to know how exactly it's done. So iterators allow me to walk down or look at individual elements in my containers, get the next thing in my containers without having to know how it's implemented. It's a really nice way of abstracting that idea. And then finally, we have this group of algorithms. These are things like the sorting algorithm, like binary search. I'm trying to think of other ones. There's got to be a lot of other ones. Random numbers, I think, are also in there. The seeding of random numbers. There's a We could go through and I do a search if I was looking for what kind of functions or algorithms are available in the standard template libraries. Sorting and searching is what we're going to be doing here. But let me also point out, I have not developed all of these things. I have not implemented a set, for example, in C++ using STL. Why? Because I haven't needed to use a set in using STL in C++. I've used other things. This is one of those cases where you use it when you need it, not before, not after. You don't memorize all of this stuff. It is meant to be, it's a toolbox that you can use, you can pick up a tool for. And we know what the tools are. We've gone over at least some of the tools in the previous lectures, and now you can just pick up and use those tools. So that's what we're looking at. So going to containers, a sequential container are things like vectors and lists. Vector not being the mathematical term, but as in it is gonna act like an array that dynamically resizes itself. So it can only be refilled at the end. It's acts like an array. I can access individual elements, so I can go to element 2 or element 17, but if I run out of space, it automatically makes me a bigger array. So effectively, it's an array, but when I only add to the very end of my array. There's a reason for that, because if I add to the front of my array, because it's an array, and because I have to keep everything in order, if I added to the front of the array, it would mean I would have to shift over everything else in my array. This is one of our fundamental things that we're always worried about. So let's do 7, 19, 20, 4, 6, and I'm going to add another value. It's going to be, let's say 5. If I added the value 5 here, I'll erase it. What would happen? Well, and I want to insert it in there, so I want to keep the 7 as well. Well, that would mean I would need to shift the 7 over 1. I need to shift the 19 over 1. I would need to shift the 20 over 1. I'd have to keep on shifting until I got some other value here. I can't just stuff it in there. I can't insert where I'd have to move all my memory over. This is actually just a contiguous chunk of memory. So I can't actually put it there. What I could do in real time, without having to move anything over, is just stick it in there. I can actually stick it at the end of my array, constant time, just go to the last element and stick it in there. And if I run out of space, I will have to do that fancy array reallocation. I make a double-sized array, put that new element in there. Copy all my old elements over. So I might still have to do that, but the vast majority of time, I'm just inserting at the end. So it's dynamic. I insert at the end. Our list in the standard template libraries, or the STL, is a doubly linked list. It works just like what we talked about in class. So I have a previous, I have a next. I can get the front or the end of the array of the linked list. Unlike what we did, you can't get to some middle element. It's not in sorted order or anything like that. It just stores stuff, and I can insert at the front or I can insert at the end. But they're in sequence. The order does matter. An associative container is something like a set. A set does not have to have a particular order. In this case, they are ordered, I guess. Their elements are sorted. And there is a key per element that can only appear once. So essentially, a set, much like a mathematical idea, there's not supposed to be an ordering. They're not supposed to have any duplication, but you don't really care about order. This happens to put it in an order, but for sets in reality, you're not supposed to worry about order. So it stores stuff in no particular order, and you can't have duplicates. Effectively, they happen to be in sorted order, but that's not the original point. That's not the primary purpose. And then there's a map, and a map would be something like what we had with our hash map. So I will get a pair of values here. So 1, 2, 3, 4, 5 is the number, and then it might be some other element might be um, just for argument's sake, it might be a pair of numbers like this is a student's ID, and that's student 1 is an associated data. So if I look up this particular number, I get student 1. I get these pairs of elements, and they can only appear once. So it allowing me to have these pairs so I can have a bunch of quick lookups. I haven't actually used a map myself either in the STL. All the our STL lists, so our list, but also vectors, and also I think they have stacks and queues and a bunch of other things. The STL list has these functions. It has a back, it has a front, it has a pop back, it has a pop front, as in remove the front, remove the back element, put on the front element. This can't be it cannot be a vector. It has to be just only a list. But a stack and a queue would also be like this. And I can get the front element, I can get the back element, I get the size of my array, I can check if it's empty. These are the kinds of things we did before. And it turns out any of our major containers all have this. I can add something to the front, I can add something, I can remove from add something to the back, I can remove from the back. I can get the front, I can get the back, these sorts of things. All sequential, I guess vector also does this, but vectors are not meant to really, you're supposed to add to the end. Push back. So that's why vector implements that one. I only add to the end. What I'm trying to get is that all containers in the STL have the same kind of methods. I can call push back to add an element to a vector. I can also push back to add an element to a linked list, or push back to add an element to a stack, or whatever the case. I'm trying to get the same functions in all of these different containers implementations, these different containers types, so that there's a consistency in how I access things. And most of these are replicated in other containers classes. So all containers actually have a way of getting the beginning, an iterator, we're back to iterators again, and an end. I can get the iterator at the end. Doesn't matter what kind of thing it is. Is it a vector? If as long as it's a sequential container, there's a start and an end. So if I wanted to walk down and check every element in my vector, I can do that. I get the beginning, I get the end, and I just keep on getting the next. I increment my iterator and I'm at the next position. I can erase at a particular iterator, erasing from the iterator. So it's erasing the element that's pointing to by the iterator, and returns the iterator at the next element. It is the next. I just move it over by one and say that this is the iterator at the next position. I can erase a range of iterators. I can have a starting iterator, an ending iterator. So, and between those two iterators, so let's do starting, ending, erasing everything in between. And it's going to return this element here, the iterator to that element there at the end. And then I can actually insert an item, and it would be positioned at wherever this iterator. So I pass in an iterator, it's going to add this item at that location. I'd have to check to see if it's adding it before or after. I presume it's adding it before so it's pointing to this iterator, it's presumably adding the element just before it, but I would have to double check, just like I always end up doing. So I wanted to go over vectors because they end up being one of the more useful, the more readily used ones. So a vector, hey, look, we have templating all over again. A vector takes in It's going to be under the hood, it's some kind of array, but it's an array of this type of object, a object type T, right? It's storing a bunch of T's. And so my vector can start off with an empty, it's not actually an empty vector, but it'll have a default size. I could say it's going to be size 100 to start. That's nice. I could say it's going to be size 100 to start, and every single value in that vector has this value. So every single, I have an array, I have a vector of integers. I'll show you an example of that, of size 100. So there's 100 elements there, and it starts off with every single one of those elements being, let's say, 2. So I have an array of 200 elements, or the vector has 200, has 100 elements, each with the value 2. That's what I said. Or I can also just start off with the size of it and an iterator that I'm going to be dealing with. And I think that's going to be our blueprint iterator, or it could be where we start things off. This also works for lists and queues, and you can actually use vectors to make a list or a queue. I haven't actually tried it with the iterator approach, but it would be one of those things I'd play with. So the value for default vector, if I don't set a default value, the default value is equal to 0. So if I make a vector of size 100, it will be 100 zeros. So it's dynamic. If I add too many things, it doubles capacity. There is a capacity value. It's the maximum number of items I can store. There's a size, which is the current number of items I have stored, and I can actually access it with my array, how I would normally with an array. I can use this thing here. You can, and you add elements normally at the end. You add and remove elements at the end of the list, normally. So if I add something in the beginning or in the middle, I have to shift everything over afterwards because I have to keep it in order. These are sequential containers. So I have to keep the order. If I remove something at the front, I got to shift everything over to fill in that space. And for our lists, we have doubly linked lists. They're constant time at the front or the end, as in I have a pointer to the front or the end of that list, and I can just add something. I don't have to walk down the list. But other things I might be needing for a linked list, I might need to be inserting in the middle, but I might need to figure out how many elements I have, which requires me walking down my linked list, the entire linked list. It might be finding an element in my linked list, that sort of thing. We looked at linked lists fairly frequently, so just all the stuff we talked about before, STL actually implements it. They even have iterators for that linked list, so I can walk down my linked list. And then, as I said, we had iterators, we had containers of various formats, and then we have algorithms. And in terms of algorithms, we're going to mostly be looking at sorting, searching, but there's even copying and modification algorithms. So whether you can modify a group of values, like add 20 to all elements or something like that. So these are not global functions of the container class. So it's not, the sorting algorithm is not an element or an aspect of the container class. I can pass in a vector and have it sorted. I can pass in an array and have it sorted. I can pass in a linked list and have it sorted. The sorting algorithm works for all possible container types that I can throw at this thing. I don't have to worry about this is the sorting algorithm for vectors. Oh, and this is a sorting algorithm for linked lists. The thing you would think that you would need that because these are radically different containers. They're holding different things. They're holding things in different ways. Like a linked list is not the same as an array, but because I've implemented it with templates, I actually don't need to worry about that. And with iterators, I just can, if I can get the next element one after the other, and so I need some kind of iterator. If I can get the next element, and if I can compare if one is less than the other thing, one thing is less than the other thing. So can I say like a at position I is less than a at position j? I need to be able to implement this thing here, the less than operator, And I need to be able to say I need an iterator. Or some means of iterating through my data structure. Then I can call one of these algorithms. And that's actually what we're going to be doing in the lab. We're going to make giant arrays of elements, throw them at a sorting algorithm, and seeing which one goes faster. That's the homework. In the labs, we will make giant arrays of giant sorted arrays, and find a particular element the fastest, whether I do a linear search or a binary search. So something to look at. So we're going to do a quick exercise. So before we go to the exercise, let me actually show you some of this stuff in action. So it's going to keep, yep, there we go. So this is the old code from last term, but I figured I already gave it a test drive, so why reinvent the wheel here? Here I'm going to make a vector that's going to store a bunch of integers. So the template says they're storing integers in this vector, and here is the name of my vector. It's a pointer to a vector, and here's my constructor. I'm starting it off at size 5, and every element that I make in this thing is going to be defaulting to the value -1. So it's going to make an array of 5 elements all with -1 for each of the positions. Then I'm going to add the number 4, the number 3, and the number 2 to my array, to my vector. It always adds to the back. Heck, let's try this out. P-vect, and then I can say push, and push back. There's no push front. There's no anything else. I cannot insert. I don't know if does insert work? What does insert do? It takes an iterator and I insert it at the iterator. But I can't like push the front or pop. I can only pop at the back, right? It's on purpose for vectors to look that way and act that way, because it's faster to do it, to add and remove elements at the very end of an array. If my array is too small, then I double the array. So I can get the size of this. I'm going to put a breakpoint on this thing just to show you in action. I'm actually expecting size 8. This will make 5 elements, all -1, and then I added 3 more. Okay, but I can also access individual elements, like here. I can get the value of the vector at position 5. I can get the value at position 2. I can set the value at position 2. Let's see what else I can do. So p-vect, and then I can put, can I put the breakpoints here, is equal to 9. And I think, is that actually going to let me? Getting directly access via this is pretty good on its own. I'm pretty impressed that it could do that. So I don't know if that's actually going to be working for me. I think I need to go through the add method. But it's essentially allowing me to go to the individual element in my array, just the same as I do with square parentheses for an array. So I can jump to individual elements of my vector without a problem and in constant time, which is quite nice. Okay, so I can get the iterator where I start my vector. This is the first element in my vector, and I'm going to get the iterator that points to that first element of the vector, and I'm going to call it IT. And as long as IT does not equal to the last element of my vector, I'm going to just store some value for val. If I dereference IT, it'll get some value val, and then I'm going to increment IT. So all I'm going to do is keep on moving one step, one step, one step. This IT, the iterator, is actually a pointer to the array that this vector has. So it looks like an array, it acts like an array, except for when I run out of space, it doubles the size. And it has all these functions, just like all my other sequential container sequential container classes that do the same thing. They have the same methods. And that's the nicety about it, is that there's sort of a consistent way of accessing these data. All right, then afterwards, just for fun, I'm going to print out the data for each element of my array, my vector, I should say. Jeez. I'm going to print out each element of my vector, and then I'm going to be done with it. I probably also should call delete. I'm not sure if I called delete on this thing yet. So I did not. So let's call delete at when I'm done with it. I'm done with this thing. So and what did I call it? Pvector. Oh yeah, that should do it. All right. So let's compile it. I hope, and I hope it doesn't blow up. I have a breakpoint right here, and I can get my vector, the size of the vector, and I'm expecting the value 8. So let's actually have a quick look at what I'm going to get here. I'm going to look at pvec to see what I have inside of it. So here is what my vector looks like. Here are all the data in it. I have this array with 8 elements in total, 0 to 7, right? And I put in the first of them are all -1 because I said that was the default. And then afterwards I pushed on a 4, then I pushed on a 3, then I pushed on a 2 in that order. And the vector size is actually 8. So I can then say, okay, well at position 2, 0, 1, 2, this value right here, I'm going to make that 17. So let's hopefully that's going to work. Hey, it worked. Great. And then I'm going to get the value at position 5. I would expect that to be the value 4. Value is equal to 4. Great, as I expected. And then I'm going to get the iterator at the beginning. So let's have a look at what the heck that thing looks like. So let's close that up. All right, here's my iterator. It is pointing to -1. And I can keep on walking around. What I should see is it'll go to, at some point in time, it's going to go to that 2 or that 4. I'm sorry, it was 17 that I put in there. I'm now at the 17 position in there, and I can go to the next one, and val is now equal to 17, and I can increment it, and I'm pointing to the next element after that, which is a -1, and I can keep on going until the last element is equal to what I'm looking for, is equal to the end, and then I'm done. So I could do the same thing. If I continue this going, I'll just output the value, whatever the value was, and then a dash afterwards. So if I continue, there we go, and wrong one. Here we go. Here's my vector: -1, -1, 17, -1, -1, 4, 3, 2. Okay, so I have a task for you guys to do, and then we're going to stop, and then I'll start another video afterwards. So I want you to see if you can come up with a way of testing if an array is out of order. This has nothing to do with the standard template library stuff. It has everything to do with our next lesson, and I want you to think about it in advance. So the function is going to be called out of order. So it's almost a question mark, but maybe it's index out of order, something like that. Maybe that's a better name for it. You can feel free to change the name if you want. So it takes in parameters that are an array of doubles, so that's one of the parameters, and an integer, which is the size of the array. It's going to return, all right, and so I have an integer array, and I have the size of my array. It's going to return an integer at the end. That integer is the first location when the numbers are out of order. Okay, so let's walk through that. What I'm expecting, if it was in order, would be that A0 is less than or equal to A1, which is less than or equal to A2, which is less than or equal to A3, all the way down. The element before me is always smaller or equal to my value, which is always smaller or equal than the next value, which is smaller or equal to the next value. Okay, so the first time that those numbers are out of order, I want to return the index where those elements are out of order. So the first place where, if it's A2 is not less than or equal to A3, then I'm going to return the value 2, I do believe in this case. If everything is in order, I return -1, as in the index where it's out of order. There is no index where it's out of order. -1 is the index where it's out of order, as in it's not out of order at all. It's in order. So in this case, here's an example. I have an array of size 10, and the place it's out of order is right here, in case you didn't see the already bolded text as well, right? It goes greater, greater, and then dips down afterwards. That's the first place it goes out of order. So I'm going to return the 3. I could have also returned the 2, depends on your philosophy on this one. But so I'm going to return 0, 1, 2, 3, and here, so we're returning the 3. Uh, and if the array ends up being sorted or ordered, I should say, then I'll return -1. So I'm going to leave it at that. I want you to actually try this exercise out because it's going to be critically important for what we do next when it comes to sorting and searching. You understanding how things being in order work and how I'd find something in order is absolutely paramount for how we think about or work through the next set of problems. Okay, so with that, I'm going to take my leave of you and have a great night, guys. Keep safe.